Now we're going to talk a little bit more about what it means to actually have an inverse. So, and a little bit of our notation for inverses. So suppose we have q, we're leaving our f's and g's. Suppose we have a function q, and q is a function of t. So q equals f at t. Suppose that's a function with the property that each q determines exactly one value of t. Now this is different from what we have said before. Before we have been talking about to have a function, each t has to create exactly one value of q. We can only use the input once. Now we're saying, well, what happens if not only can we only use the input once, but suppose we only can use the output once? If we can use the input only once and the output only once, then what we would say is the function has an inverse, and our notation looks like f raised to the negative 1, but I will remind you and remind you and remind you, this does not mean the same thing as 3 to the negative 1 would. This is just the notation we use. It means the inverse of f. So if we use each t only once and each q only once, each input once and each output once, then our function is going to have an inverse. And the inverse is actually almost thinking of the function being reversed. So notice our input on the inverse function, our input becomes q, so f inverse of q, and our output then becomes t. That will be correct. We will actually be able to make that statement if and only if q is a function of t. So we would need to start with a function and end with a function using the input on the original function only once, the output on the original function only once. Think about it. You can't reverse a function and get another function unless the new input is used only once. So again, what does this really mean? Each q determines exactly one value of t. Again, it means that not only does each domain item t produce exactly one range item q, but in the original function, each range item q is matched with only one domain item t. We can use each one only once. Some of you may remember from your previous math that what we say is the function is then one-to-one. We'll be using that phrase as we go through the section in the course. But basically one-to-one. We use each x once, use each y once, use each input once, and each output once. So what we might realize then is some functions don't have inverse functions. And probably the one that we think about the most and actually misuse the most is f at x equals x squared. Right? You think, well, why aren't they inverses? We have x squared and the square root. Don't they cancel each other out? Well, technically, they are not, f at x squared is not invertible. It doesn't have an inverse. Because if I think about what happens when I get out the number 4, for example, we actually know that we have two numbers that would produce that output of 4. Right? F at 2 would be 4, but so would f at negative 2. So the problem is our function is not what we call this one-to-one. We have output numbers that have more than one corresponding input number. If f had an inverse, then the fact that f at 2 equals 4 would imply that the inverse of f has to take the number 4 back to 2. And what we know is it doesn't, that the number 4 could go back to 2 or it could go back to negative 2. So technically, f at x equals x squared has no formal inverse. Some of you say, well, wait a minute, I've done that before. Well, usually in order to do that, we do what's called restricting the domain. We talk about the inverse of x squared only when x is positive, or only when x is greater than or equal to 0. And so what we do is we restrict it so that we can actually talk about inverses. Again, remember, for a function to have an inverse, it must be one-to-one. So by definition, a function is one-to-one if each element in the domain is mapped to exactly one element in the range, and each element of the range is mapped to exactly one element in the domain. So 1 to 1.